I have Boob Mode Jiggler. Oh, you guys don't. All right. So, where is my stuff? So this is where we start to get some crossover with Science 10, specifically physics, and Physics 11, okay? Understanding these graphs are bread and butter of physics, okay? So, let's work through. You shouldn't need me. It's the remix. Wrong one. Wrong one. Story of my life, Joel.
Yeah.
Alright. So, Preeti Randhawa brought me these gums she says comes from India. They're delicious. We used to have them in Canada. They were called Freshen Up, but they stopped making them. She's like, I hate these. And I'm like, oh my God, I love those. When I was like 8, they were awesome. And then they didn't have them in Canada for a long, long time. She says she has a giant bag of them. I'm hoping she brings them to me. They're delicious. They're gum, but in the middle is a big glob of syrup. So it's kind of grody for a second, but then it's like yum, and then it's like gum. But anyway. What are the independent dependent variables? IV, DV. Which is which? Time is IV. Now, Alon, are you saying time is IV because I said somewhere in your notes that time is almost always IV? Or are you saying time is IV because you know that time is IV? Why is the time IV? Yeah, the depth depends on the time. He's a scuba diver. The longer he is diving, the deeper he can go. Meanwhile, he has a support team on the boat, doesn't he? Are they going down to any depth?
Nope.
But is time still passing for them? Yes. Okay. And also, you will notice the way this is written. Depth as a function of time. So time must be the input, right? So our dV becomes our depth. Then the rest of this is just reading the graph. How long did the dive last? 30 minutes. How did you know? Because we go up in 2-minute chunks, right? And he is back at 0 depth, which is the surface, at 30 minutes. Now, next, at what times did the diver stop her descent? So on her way down into the water, she stopped. How many times? Twice. She found Nemo. Okay? Which, of course, by the way, is the second most frightening incident in all of cinematic history. In Finding Nemo, where he swims around the corner and finds his entire family murdered. Finding Nemo should have been rated 14 years. It opens with a mass murder and a kidnapping by giants. The first one. Everybody talks about how cute it is until you think about the first 5 minutes. Damn right it's messed up. All right, let's carry on. So, when did she find Nemo? 4 minutes to 8 minutes. And when? 10 to 14. How do you know that she was stopped then? It's a flat line. Now, there's a problem here. A great many of you, when you are reading these graphs or making your own graphs, forget something about the nature of time. In our universe, time marches on in a linear fashion. It doesn't stop. Therefore, you must remember to connect all parts of a graph when time is part of the function, because time can't stop. What is the other thing time can't do in our universe? Go backwards. So can your line, if time is your domain, ever go to the left? No, unless you have a 1985 DeLorean with a flux capacitor, which none of you do. Although I heard that DeLoreans are coming back. If you want to do some very interesting reading, and you don't want to watch me on YouTube, and you don't want to watch anybody impale their genitals on picket fences, you should look up the history of the DeLorean car, the car from Back to the Future. They should have made a movie about the guy, DeLorean, that tried to make the car the DeLorean, because that guy is bad news. It's really cool. I didn't read about it on the internet. I read about it in my Uncle John's bathroom reader. But you guys, being kids, don't want to read anything in a book. So, check it out online. It's very cool. What was her greatest depth? 20. Shut up, Jim Warren. This isn't easy, you know. Drawing all this and keeping up a snappy pattern. It's not easy. 20 meters. How long did she spend at that depth? 4 minutes. And finally state the domain and range. This is weird, because can you use X and Y? Why would we not use X and Y? Because they're titled. It's time and depth, isn't it? So the domain, which I like to do in blue, is what? It's the independent variable, which in this case is time, right? It's not X. And it's a set. What does it look like now? What is the only thing time's allowed to be? 0. T for time, up to what? 30. Are there any restrictions on that? Does time ever stop?
No.
Is there always a time? So there's no restrictions, is there? So we're done. Because I can be everything in there. I can be the root of 7 minutes, can't I? Cool? Alright. What's range? Depth, such that, what is my depth allowed to be? 0, D, 20. Did she teleport between depths? No. She passed through every possible value of depth, didn't she? So is there any restrictions? No. Everybody got it? Everybody got it? Okay. Right. I know it's math class, and I know that this hurts some of you. But you must do it. You can write it in point form. It does not need to be flowing, beautiful prose. But explain to me this graph in words over here. Okay? I'm going to give you one hint. Go! I will hum the Jeopardy theme twice in my head. But I won't do it out loud because that stresses you guys out. Should I do one more Jeopardy theme? Everybody good? All right. Would anybody like to volunteer their scenario for what happened to the water? No one? Super Green, hit me. For part of that graph, they are emptying the can. First, they fill the can. Was the can empty? No. So, Parveen.
The volume of the water is increasing in the watering can due to rain, but then it's just evaporating.
I like it until the evaporated part. And we'll talk about why in a second. Kobe.
The water's volume is 1. In 30 minutes, the water's volume is
30 minutes?
20 seconds.
That's okay, but carry on. The volume increases.
The water increases to 1.75
Uh-huh.
and stays there for 40 seconds.
Mm-hmm.
In 20 seconds, it then gets bubbling.
Okay. Excellent. That's what happened to the water, yes? Was it a particularly interesting scenario? No, but this is math class, not English class, isn't it? So it's perfectly acceptable, yes? Right? There's a watering can, it's got some water in it. Right? They fill it. Then it sits for a while, then it gets emptied. Right? We can jazz it up a little. Right? Well, the watering can was sitting there, and then I took it over to the sink, or to this hose, and I filled it up a little bit, and then I walked over to my garden, because the water stayed the same, and then I emptied the water. Understand? But there's some more stuff to be happening here. What do you notice about this line compared to this line? It emptied faster than it filled. How'd you know that, Michaela?
Because the filling is stretched out over time.
Right. Even if you haven't done physics in grade 10, this just makes sense, doesn't it? This time to fill only a little bit of the can took 30 seconds, didn't it? But emptying the entire can only took how long? 20. So what does that tell you about lines on a graph? That should tell you something. This line compared to this line. How would you describe them? Just using your words, don't use math. How would you describe the difference between line segment AB and line segment CD? CD is steeper. Makes sense, right? Which of those lines would you rather roll down on a skateboard? Well, of course, all the boys say CD, but really, AB, because CD would kill you, right? Okay? AB, that's your green circle ski hill run. CD is your black diamond. Understand? Okay, we'll talk about why later. I just wanted you to see that. The steepness of the line means something. If you've already done physics in Science 10, you already know the answer. But if you haven't, keep it in your head. Got it? Okay. So of course, happening to the water, it fills slowly from 0 to 30 seconds, stays full 30 to 70 seconds, and then it gets emptied quickly from 70 to 90 seconds. That's what happened to the water. That's all I need, right? Could you gussy it up and make it a fun little story? Sure you could. My sister was by the water and by the plant, so I dumped the water on. I don't care. Okay? But do remember, I like a good story. Everybody cool? Everyone can read a graph? Great. Now, let's see if you can actually do it. Draw an accurate distant versus time graph to show the following scenario in order. Everybody ready? You can work with your buddy. I'm going to give you like 5 minutes to do this. Oh no, Joe, whatever will you do? Oh, Mitchell's in trouble too. Maybe you guys can solve your problem.
You know, sitting up here, I totally forget about everybody behind me. I don't even think about that.
You really don't want to say that out loud, man. That's pretty egocentric.
Yeah,
You want to probably not say that.
probably not.
Yeah. Okay. Go! Sketch it lightly in pencil because you're probably going to make a mistake. I'm going to sit up here and drink my coffee. Am I going to be humming the Jeopardy theme? No. But I am going to pause our recording. All right, we are recording again. So, distance goes up the side here, yeah? Who decides on the scale? You guys. I'm going to say that's 25s. So 1, 2, 3, 4, there's my 100. Everybody cool? All right. Time, hours. 1. Do I need to write more than that on my graph scale? No. I'm a math teacher. If I can't figure out that 100 divided by 4 means each tick is 25, I probably shouldn't be here. Yeah? Okay. Same thing down here. All right. So how does this graph start? What is his distance from home, and what is his time when the graph begins? 0, 0. He starts here. Yes? Because the time hasn't started yet, and he is at his home, so he is no distance away. Yeah? All right. For the first 2 hours, amazingly, he lives apparently on a freeway because he can get right from his house and immediately travel at a constant speed. Okay? There's no stop signs, there's no lights, there's no pedestrians. Apparently, he just jump and he's going. Whatever. So for the first 2 hours, So 1, 2, he goes how far? 140 kilometers. So 100, 25, 50. Now, the fact that it is constant, what does that mean? The line is straight. Did everybody do the first part right? Excellent. What happens when he gets to his grandma's house? It's flat. Why? Because he is not changing his distance from home. But, just like Metallica says, time marches on. Okay? Anyone? Metallica? For whom the bell tolls? Kale, you got it? Time marches on! All right. I'm glad. So for 1 hour, is flat. Yeah? Everybody cool? Is everybody still okay? Now, he drives 50 kilometers back home. Now here is where you're gonna screw up. Okay? Where does the line go from here? Does the line go up or down? Please notice the word I double highlighted in the question. It's not displacement.
I see.
What is it? Distance. How many of you have seen Ferris Bueller's Day Off? Does the odometer on the car go down when he rides backwards? No. The car is still traveling a distance. So where does this line go? Up. For 50 kilometers. Does it specify a time? No. So, we gotta go up, and I'm gonna change to red because this is where people get screwed up. For 50K. We don't know what's happening for the 50K, so I'm just gonna do a squiggly little line because we don't know what's happening. And it's gotta go up 50K. We also don't know how long it takes, do we? Everybody cool? But we do know he stops for 30 minutes. So there's a flat for half an hour, yeah? Agreed? And then he returns home taking 2 more hours. Now he has gone part of the way home, hasn't he? It took him 2 hours to get to his granny's. He's gone part of the way home. And even though he's gone part of the way home, he still takes 2 hours to get back to Granny's. So is the line going to be this steep, more steep, or less steep? Less steep, because he is traveling less distance in the same amount of time. Does everyone understand? Does everybody get it? The red line is because the graph was for distance traveled. Everybody understand? Now, if I asked you for distance from home, what would happen right here? This would reverse, wouldn't it? Down, flat, home. The blue is for distance from the starting point, which has a special name in math and physics. What is it, Alon? Displacement. And that is called displacement. Okay? And I always like to do a visual aid here. Where am I? Starting point. Okay? 0. What direction is positive? Forward is one definition of positive, which makes negative what? Backwards. Excellent. I can go neither forward nor backwards. I have a desk and a chair in front of me, so I can't use forward and back. What are other directions? Left and right. Okay? For you guys, left is that way, and it is negative because of the number line. So, if I do this, 1, 2, what was my displacement? How far did I move from my starting point? -2. What was my distance? 2. Understand? Displacement has a direction. It is what is called a vector. Distance is what is called a magnitude, because it is just a size. Everybody got it? Now, what is my displacement? Wrong. 0. Why? Because I'm back where I started. What is my distance traveled? 4. 2 there, 2 back. Understand? Okay? Everybody good? Joel, where's my magic pen? In my pocket. To keep with the Ferris Bueller jokes, it's been in my pocket, so it's warm and soft. Anyone? The gummy bears at the end on the school bus? How many of you have not seen Ferris Bueller's Day Off? Have not seen it?
We should watch it on cast.
Let's do it. 10 minutes.
Parents, I hope you're hearing this. Remember, yes, let the record show that 90% of the class put their hands up for not having seen Ferris Bueller's Day Off. Remember, distance is a magnitude, which means it only has a value, no direction. Displacement is a vector, which means it is a magnitude and direction. Okay? Everybody cool? Right, up, east, north, are positive. Oh, I'm going to add one more. No, I'm not. Yeah, I am going to add. Away from your start are positive. So, return, left, down, west, south are negative. And that is just for convenience. Okay? Does everybody understand? Everyone is good? I'll give you another example of magnitudes and vectors. Speed is a magnitude. I am driving down the highway at 80 kilometers an hour. That is a magnitude. Okay? I am driving south at 80 kilometers an hour. That is a velocity, which makes it a vector. Do you understand? Everyone cool? Once a direction has been added, you have a vector. So, let's have a look. See if you can do what we did with the watering can for Alicia's race, and then we're going to stop. We're going to be done. So how many steps are you going to need to describe this graph? 3 or 4, right? So go ahead. Is everybody happy with that? Does everybody understand? Here are the couple of mistakes that people make. One, the questions that get asked for a graph like this is, when did the race end? Obviously it ended here at 14 seconds, because that's when she started slowing down. I don't know about you, but when I run a race, I don't start slowing down before it's over. That's the type of question they like to ask about this, okay? Another mistake that people make, well, if the race ended, why didn't she just stop? Well, she didn't run into a wall. It's not the Hunger Games. She didn't die. She got to slow down. You guys have seen people run races. They run through the tape, and then they start slowing down. And then they either cry because they lost or cheer because they won.
Or cry because they won.
Or some of the weird ones cry because they won. I don't get that. And then there's some that are, just lucky to be there and they cheer because they lost. Whatever. Everybody okay with it? Okay.